Welcome back to Math 104. Working now with our unfair four-sided die, we ask what is an ideal data set of outcomes of rolling the die and just observing the number that appears. So forget for the moment about the dollar amounts, just look at the numbers that appear. I claim that the following set of 12 numbers will work. 4 copies of the number 1, 3 copies of the number 2, 3 copies of the number 3, and 2 copies of the number 4. These 12 outcomes, I claim, form an ideal data set, and no smaller collection of numbers will form an ideal data set. So how can we think about this? First of all, notice that of these 12 numbers, a third of them, 4 out of 12, that's a third, are indeed ones. 3 out of 12, that's a quarter of them, are twos. Another 3 out of 12, that's a quarter of them, are threes. And 2 out of 12, that's 1/6, are fours. Notice that you could not have obtained an ideal data set consisting of 100 rolls because 1/3 of 100 is not a whole number. Instead, you need a number of rolls of the die so that exactly a third of them are a 1, exactly 1/4 of them are a 2, etc. So in order to dream up the idea in the first place that you should look for a set of 12 numbers for your ideal data set, what you really need to do is find the least common multiple of the denominators of the probabilities that are given. That really means that you need to express these probabilities in terms of a common denominator. The smallest available common denominator that works is 12. Once you know that each outcome occurs with a probability equal to a certain fraction of 12, then 12 becomes the clear choice for the size of your ideal data set, and you can read off the numerators as the number of occurrences within the ideal data set of each outcome. So there are 4 ones here, there are 3 twos, there are 3 threes, there are 2 fours. Each numerator is counting the number of occurrences of that outcome in the ideal data set. It is worth understanding that this is exactly what we did in an earlier example in which the probabilities were given in decimal form, in particular as finite decimals. Here they were each with 2 decimal places. In that example, we obtained an ideal data set consisting of 100 rolls of the die. But what we implicitly did, without necessarily realizing it, was that we thought of each probability as a fraction of 100. Since each of the probabilities is a certain number out of 100, that made 100 a natural choice for the size of the ideal data set, and then from the numerators we could read off that there should be 14 ones, 20 twos, 12 threes, 20 fours, 18 fives, and 16 sixes. Our next question from the end of the last video is, what is an ideal data set of payoffs of the game using this die? If we believe that 4 copies of the number 1, 3 copies of 2, 3 copies of the number 3, and 2 copies of the number 4 form an ideal data set for the numbers themselves that appear on the die, then the corresponding dollar values should form an ideal data set of the payoffs. That means in a perfectly representative 12 plays of the game, there will be 4 times that you're receiving $2, 3 times that you receive $4, another 3 times that you receive $6, and 2 times that you receive $8. If it helps, you can imagine that we've taken the die and physically relabeled it so that instead of displaying the number 1, it displays $2, instead of displaying the number 2, it displays $4, etc. But even without physically relabeling the die, it makes sense that an ideal data set of numbers that can appear on the die should correspond in this one-to-one way with an ideal data set of the dollar payoffs. In the long run, what is the average payoff per play of the game? Now that we have our ideal data set of payoffs, we just average them, add them all up, and divide by 12 to discover the average payoff per play of the game. This turns out to equal $4.50. It makes it much easier to write out this expression if we group all the common values together. So in particular, $2 times 4, plus $4 times 3, plus $6 times 3, plus $8 times 2. all divided by 12. So that equals $4.50. We'll have further use for this idea of grouping like terms in this way. The bottom line is that we can understand, on average, per play of the game, what's going to happen in the long run, just by averaging up the values in an ideal data set. Because being an ideal data set means that these values know about the long run. Again, we introduce a cost for playing the game, so that now you might make money or lose money each time you play. The next question is, if it costs $4.75 per play of the game, then in the long run, will you make money, lose money, or break even by playing the game? As we saw in the last video, the thinking is that an average gain of $4.50 per play minus a certain cost of $4.75 per play of the game results in an average net loss of a quarter, an average net loss of 25 cents per play of the game. So if you play this game over and over again, in the long run you're losing money. This is a losing proposition. That's the opposite conclusion from the one we reached about playing the very same game with a fair die. This die is weighted in favor of lower outcomes and therefore lower payoffs. Our computation must account for this. Before going on to the next video, answer the following questions, which involve your personal preferences, so there are different possible answers. Would you play this game once with the unfair die at a cost of $4.75? Would you play this game 100 times with the unfair die at a cost of $4.75 per play? And what is the greatest amount that you would be willing to pay per game in order to play a very large number of times using the unfair die?